Yeah, sure, please.
So announcements. We're gonna get started. Real quick. We've kind of looked back on all the assignments we've given you guys and decided that it wouldn't be reasonable to give you like a final assignment. So don't worry about that. So you can rest easy. No final for dead week. Make sure that all your assignments thus far are in, and they're all forks of the repos, so we can check them. Because we're going to be submitting your grades by mid-dead week. So keep that in mind. So continuing in our 2-week session of guest speakers, we have someone from O1 Labs here. Do you want to talk about what you're going to be talking about today?
Yeah. Okay. So I'm Isaac, or you can call me Izzy. What I'm going to be talking about today is basically, well, okay. So last class I believe Howard spoke to you guys about zero knowledge proofs, right? Is that right? Everyone say yes. Okay. So that's a kind of technology for proving some kind of statement to someone, but the way things are written, it's sort of right now in a very primitive state. I mean, knowing that the proof you construct really proves the thing that you want, it's a bit like looking at an assembly program and trying to figure out if that does what you want it to do. So things are sort of equally primitive. But now I guess we did there was already 50 years or whatever of computer science. I mean, of programming language development after assembly programming. So now we know how to do things better anyway. So things can go faster. So that's what I'm going to be talking about. Let's get into it. Oh, so yeah, rules. If anyone has any questions or wants to know about anything, please interrupt me. Because does everyone? Someone interrupt me. All right. Okay. Right. So external motivation. I mean, the view from outside, people who don't already care about this. Howard probably went into a bit of this, but there's this idea of verifiable computation, which is you want someone else to do some computation for you, and you want to be confident in the result of the computation, but you don't have to redo the work yourself. So this is a really crazy idea. I mean, there's a lot of awesome applications. Some I'll just rattle off the top of my head. You can have private auditable elections, so elections which are totally private, but you can still check that the result was computed correctly. For example, you can sort of offload computation trustlessly to cloud providers. So right now you go to Amazon and you run some computation on AWS or whatever, and well, probably they run it correctly because they seem to be relatively trustworthy, at least in terms of providing that service. But in the future, that might not always be the case. So it would be cool to be able to get some evidence. They don't just hand you the result of the computation and say, here, we did it. They actually give you a proof that says, we did the computation, and here's proof that we actually did it, as you specified. Another cool one, and this is kind of what we're working on, well, actually exactly what we're working on, is so-called blockchain compression. So this is the idea that, right now, I guess you guys know something about cryptocurrencies. If you connect to, try and sync with any existing cryptocurrency, what happens is you try and download the entire history of the world. And that's kind of your proof that the current state is what it is the whole transaction history. And then you go and you look for yourself, okay, here's how much money I have. But it doesn't need to be this way. So what you can do instead is you can just send someone a proof that says, hey, all you cared about was what your balance is. Well, here's a proof which says there exists some super long blockchain such that your balance, according to it, is 50 bitcoins or whatever. Instead of having to download the whole transaction history, you just have to download a little proof instead. Right. So this is exactly what I just said. I guess I'm jumping the gun. So I am working at this company, O1 Labs, on such a blockless blockchain or compressed blockchain. So I basically explained it. So you can sync instantly. It means everyone is actually verifying instead of delegating trust to whoever happens to be storing the full state, hopefully. Okay, so a bit of background on SNARKS. I guess you guys heard about this, but what is a SNARK? So a SNARK is a succinct, non-interactive argument of knowledge. Okay, what is that? It's a short and easy to check. So succinct means short and easy to check. Argument of knowledge means proof. Non-interactive means, there's no interaction. Okay. It's a proof or a statement of the form. There is some data, and actually, moreover, I know some data such that some property holds of that data. Okay. So what could be an example? There is some blockchain such that it's a valid blockchain, and your balance is whatever. Another example. There are votes. Well, okay. Anyway, maybe let's just stick with that example for now. But as a sort of special case of this, if you just ignore the there exists part, it also just lets you provide proofs for the correctness of computations. So you can also just not use the there exists. Maybe I shouldn't even go into that. So very briefly, a background on these so-called rank one constraint systems. I think Howard also touched on this. I'm not going to, this is really not going to matter that much what I'm about to say. So it's only if you care. I don't even know why I'm saying it. So a rank one so who knows what a field, does everyone know what a field is? Probably not. Does anyone know what a field is? Okay. So, it doesn't matter. So a field is just think like integers, okay? Forget fields. Just think like integers. Whole numbers, yeah? Whole integers, whole numbers, okay. So I wrote f, but here just think f is like whole numbers. Okay. Whatever. So a rank one constraint system is a list of equations of the form. Oh, I really typeset this shittily because I didn't care about the slide that much. Okay, I'm so sorry. It's a linear it's an equation of the form. Basically, just think about it like this: some polynomial in some variables, okay, is equal to some other polynomial. Oh, do people know what I mean polynomial? I mean something like, it's like x squared plus minus 5y times z, plus 17. Yeah. So an example of one of these constraints, and this won't be a rank one constraint, but an example of some kind of constraint is 5x squared minus 17, what did I write? Whatever, 17xz plus y to the 8 equals 37 minus 4 z squared y cubed or something, okay? So that's like a constraint, okay? And, a constraint system is just a list of constraints. Okay. So, once you have a constraint, there's this idea of a satisfying assignment, okay? So what is a satisfying assignment? Well, who can guess? Can anyone guess?
What is the solution to that?
Yeah, so a satisfying assignment to a constraint system means an assignment of values, numeric, let's say a whole number of values to each of the variables, such that when you plug in those values into all the polynomials, they all say true, 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 true. Okay? All your constraints are satisfied. Does it make sense? Yeah.
So this is analogous to integer programming?
Yeah. Except now we're not talking about integers. Actually, we'll be over a field. But yeah, you can think like this. So you're looking for solutions to systems of equations. There's some settings where you talk about integer solutions, but anyway, whatever. So the cool thing is, and Howard mentioned this yesterday, or last class, there are practical SNARK constructions for proving that a satisfying assignment to such a constraint system. What does it mean? If you have such a constraint system in mind, you can produce this little proof, no matter how big the constraint system could be. It could be 1 million equations long. It could take gigabytes to write down the whole constraint system. You can prove that a satisfying assignment with a few hundred bytes. Okay? A little SNARK. That's what a SNARK is. And they can check it super quickly, so in milliseconds. So you can have gigabytes and gigabytes and gigabytes constraint system, but someone can check it super quickly, okay? That values to plug in. But you don't show them the values. If you show them the values, of course, it would also be gigabytes and gigabytes and gigabytes. Okay? Does it make sense? Everyone kind of with me on this idea?
Can there be multiple assignment which can verify that as well?
Say again?
Can there be multiple solutions, multiple verification that can satisfy that equation?
It may be that there's more than one solution, yeah. But you can just prove I know one solution, okay? Okay, cool. So that, as a bit of background, now, once we believe that, it's something interesting to want to be able to prove correctness of computations to other people. Once we believe that idea, then there is some internal motivation, which is what? Which is that, oh yeah, I forgot to say, there's this fact that like any computation that you have, it's any property, any statement of the form, there is some data such that some property holds, you can express as like a constraint system, okay? So you want to prove to someone, you know, someone say their favorite algorithm. I don't know. Okay, Shor's algorithm, Dijkstra algorithm. So yeah, so you want to prove to someone, hey, I ran Dijkstra algorithm on this graph, and distance between these two vertices is 50. Okay, you can specify that as some constraint system. So the constraint system is satisfiable if and only if the computation that you're talking about actually, you know, went the way that you claim. Okay, does it make sense? So you can sort of simulate any computation with a constraint system. Okay? Everyone kind of buy that, maybe? So, well, okay, so you can, it's possible in theory to specify any computation as a constraint system, but in practice, you know, that really sucks. You say some complicated algorithm like Dijkstra's algorithm, you're going to sit down and code that up as constraint systems. I mean, it's crazy. You'll go insane. So, and, you know, moreover, this process is super error-prone. Ironically, it's once you have such a constraint system, it's hard to verify its correctness. You know, if I hand you, imagine I handed you some giant list of polynomial equations, and I said, yep, this implements Dijkstra's algorithm. Who would believe me? No one. No? Would anyone believe me? You would believe me. I'm sorry. Okay. Do people get what I'm saying? It's like if I give you a compiled binary, right? Compiled binary, and I say, this is a nice program. It will, you know, it will compute the millionth prime for you. And no, of course, I'm lying. It's going to take all of your files and encrypt them and hold them ransom for Bitcoin or something like that. You see what I mean? And it would be hard to look at the code and be able to know that. So this is a big problem. Oh, it's also super not fun. It's not fun. There is a certain joy in it on a small scale, you know, like there is a joy in, I don't know, what's something that's tedious but like kind of fun. I don't know. You ever do like little bit hacking kind of stuff, like little bit twiddling stuff? It's sort of the same sort of pleasure. But you know, and abstraction and reuse are very difficult for these constraint systems. So it's really an analogous situation to writing assembly by hand, which is like not something you want to be doing. Right. So you know, a little bit to expand a little bit on what's going on here. The cryptographer's eye view of the situation is the following. Here's what a proof system is. I want to prove some property to you. What's a property? It's a constraint system. What do? You know, a proof system turns that constraint system into a proof, like a SNARK. Okay? And there's an informal proof of correctness in some paper somewhere on ePrint that proves that this, you know, is really a proof, or you should really trust such a thing. But that's really, you know, there's really sort of a hidden security assumption here, which is, as I kind of, you know, said already, but I'm really driving the point home, I guess. There's this hidden assumption, which is that this constraint system that I wrote down accurately reflects the property that I want to prove to you. Okay? So that's like the naive or like cryptographer's eye view, but there's a whole you know, world above that. That's really just the end of this greater process of proof. Like proof really, what is proof? It has to be convincing to a human mind, right? I mean, at the end of the day. No? Yes? I don't know. When I say I prove something to you, I mean, you think you in your mind are convinced by some evidence, right? So there needs to be some kind of reason to believe there is a connection between what's in your mind and what the computer says. With me? Yeah? So really, there's this whole process of sort of compilation. It starts, you know, with a high-level spec, which is maybe in your mind, maybe formally specified in a tool like Coq or Agda. The programmer is the first compilation step. They take the high-level spec and they turn it into some kind of program or encoding. This would be like a program in libsnark. Howard mentioned libsnark, right? Yeah. Or a program in Bellman, or in the library that I'm going to talk about, which is called Snarky. You know, then how do you know that's correct? You have some either formal or informal proof that the encoding that you wrote down actually respects the spec that was in your mind. Then there's some kind of compiler or interpreter for the encoding, which turns it into a constraint system. You have to have some proof, either informal or formal, that the compiler is sort of respecting the semantics when it does this compilation. Then we go back to where we were before, which is the constraint system gets turned into a proof by the SNARK construction or whatever. Okay? Do people kind of see where I'm coming from? So here's cryptography, and here is like, you know, what people don't traditionally think of as cryptography, but is nonetheless, if you're going to call something a proof, you have to think this way. Anyway, so cool. Does that make sense, roughly? Who's with me? You look, no, everyone? No, okay. Who looks confused? No, okay, sorry. Who's with me? Maybe that's a better question. Okay, cool. Yeah, so you want to have this connection, right? So, okay. So what's the goal? You know, let's try and complete as many aspects of this picture as possible. We have super good SNARK constructions for these rank-1 constraint systems. Let's make languages that compile to those constructions, but which are nonetheless closer to our mental understanding of the situation. So here are some, you know, Desiderata that I'll propose for such a language. It should be easy to check correctness of programs. Now with your brain and with tests, and later with formal verification tools. Okay, like Coq or Agda. Things should still be efficient. So, okay, so these SNARK constructions are like pretty good, but they're still like a huge constant factor slowdown from doing just like native computation. Huge constant factor. So you still need to care how many sort of constraints are in your constraint system. So these new languages should still be efficient. They should be fun to use. And this is sort of a pun. I said fun in monospace because I mean it like functional programming. You know, it should have a type system to help you enforce correctness and make abstractions. And the semantics of the language should somehow be compositional. I'll explain more what I mean by compositionality, but it's really important for code reuse and for proving correctness of programs. So compositional, who can guess what this means? I think it's actually a pretty good word. At first I thought it was a stupid word, but who can guess? Anyone? Yeah. Anyone have an idea? Something about composition, obviously. Well, yeah. Yeah, I guess really specifically in this setting, I mean the idea that you can have different pieces, okay, and there's some means of combining the pieces, and moreover, there are some properties which are respected upon composition. So things change in a predictable way when you compose them. You know, it's not just it's not that you put two things together and you get something totally new. In other words, the whole is sort of analyzable as the sum of its parts. Does that make sense? Yeah. The whole is no more than the sum of its parts. Okay. So here's like a proposed language. So this is Snarky. This is a language that you know, as I said, we're doing this blockchain compression thing, or this tiny blockchain thing. It's a really complicated computation, relatively complicated computation, verifying a blockchain. You can't really do it by hand with constraint systems. You'd go insane. So we developed this little programming language called Snarky. It's a simple functional programming language. You know, I don't know how many programming languages people there are in the audience, but it's really, I mean, at its core, it's really simple. It's sort of just like simple kind of Hindley-Milner style programming language that's like Haskell or Camel, like the simplest core of those languages, plus like tuples, and then there's this cool request and handler system that people know how to program, right? By and large. Yeah. Okay. That's cool. So yeah, then there's this request and handler system and assertions for modeling non-determinism, and I'll say what that means exactly. So so it's actually implemented as an embedded DSL in OCaml. DSL means domain-specific language. Embedded means like it's actually inside of an OCaml program. Okay, but I'm not going to talk about that. I really just want to kind of get across the main ideas of the language in case like you're like, hey, I'm gonna, do some SNARK programming. Like it's more important, I think, to have these ideas than to know how to use the library. There's other, you can go online for that. So so I'm going to use like an idealized syntax, which is not the DSL syntax. Why? Because inside of the DSL syntax, you have to deal with OCaml noise. You know what I mean? It's not a perfect fit, so there's a bit of friction. So, okay, so what I mean, Hindley-Milner with tuples is sort of the base language, simple functional programming language. Who's familiar with the concept of like functional programming? Sort of. Okay. Would people know what this function is over here? Fun x arrow x. Does it parse? I mean the function like that takes x to x. Okay. So that's what. Okay. And then so you have functions. Function application. Sort of left binding, so you can bind intermediate variables. Okay, of course, it's a programming language. You say, oh, this intermediate value is the result of this computation, and do something else with this intermediate value. You have tuples. Okay, so that's sort of simple functional core of the language. Now, what's interesting is, by the way, so yeah, this is a language which compiles to these constraint systems. I don't know if I made that clear, but that's the deal. So what's more interesting is this idea of a request. Okay, this is a really, I think, nice and simple way of thinking about what you're doing inside of a snark. So what do I mean request? I mean what this picture implies. Like the idea of a request is the computer is somehow stopping its execution. The program is somehow stopping its execution. It's sticking its hand out. Okay? It's asking, please, someone out there, put a value into my hand, then I'm going to take that back inside and resume computing on that value. Okay? Does it make sense? So it's kind of like throwing an exception. So this is a nice way to think about it. It's a generalization of the idea of an exception. When you throw an exception, you're saying, hey, I'm done, right? You put out your hand and you say, I'm over. Someone else, please resume computing. Okay? Yeah? Here, you say, I'm done for now, but as soon as you give me something, I'm going to keep going. Okay? So it's a really nice construct. Hasn't found its way into any mainstream programming languages yet, but soon. So, right. So, well, we'll get into that later. Okay. So the syntax for this is the following. I hope this kind of makes it concrete for you guys. This is how you declare like a request. You say, oh, I have a request. It's let's do this one. It's solve this Sudoku. Okay. And it takes a Sudoku board as an argument, and it produces like a Sudoku solution. Okay? Does that make sense? And so, when you declare this, you get a function called solve Sudoku, which takes a Sudoku board and produces a request for a Sudoku solution. Okay? And then you can sort of call that request using this request function. You say request solve Sudoku on my cool Sudoku solution, the puzzle. Okay? And what that's saying is like, it's like throwing an exception. I'm like, execution pauses. Someone out there is going to stuff something in, and I'm going to resume computing on that value. Okay? I said, hey, someone please give me a Sudoku solution to this puzzle. They take it, resume computing. Okay? Does it make sense? Somewhat. I'm okay. Should speed up. So, and then there's also, let's just stick with that example. So, then, once you have the idea of a request, you need to somehow have some mechanism for handling a request. This is like an exception handler. As I said, you say, oh, I'm sticking out my hand. Someone please put something into my hand. Then someone has to, you have to somehow specify in the code how someone puts something into your hand. Okay? So, this is similar to exception handlers. Whatever. This is kind of, so, okay. So, here's the syntax. You say, okay, handle my cool computation with, if the computation throws a request for solving Sudoku puzzle called puzzle, you should respond with the solution that you get by doing an exhaustive search for a solution. Does it make sense? So there's this kind of interactive feeling, dynamic feeling process where there's sort of what's going on inside. There's like a little box, okay? The box chugs along. occasionally it sticks its hand out and says, hey, someone please help me out there. Someone out there does something complicated and puts something back in, and the box resumes. Yeah? Okay. And so, okay, and then you can make assertions. You can say assert this is equal to that. Okay. Anyway. So, what did we talk about before? We talked about these constraint systems. And what we prove for a given constraint system is, I know a satisfying assignment to this constraint system, right? So now the question is, we can write these programs, but what is it that they're proving? What you prove is, let's say you have a snarky program P. You want the snark that you get out of that to prove, I know values of the appropriate types, so that, to answer every request that the program makes, so that the program can execute without an assertion failure. Let's make it concrete. This will be a contrived example. Do people know what SHA-256 is? It's some hash function. Okay? Now, when I say SHA-256 preimage, so SHA-256, when I say preimage, like a preimage of, y, this is some x such that it hashes to y. SHA-256 on x is y. That's what I mean preimage. Okay? Yeah. If it helps, the picture to keep in mind is like, here's this. People know about this, I guess, but here's SHA-256. It maps this space into this space. Here's here's y, and then there's some x up there, which is a preimage. Maybe there's more than one, which hash to y. Okay, so that's what I mean preimage. So let's make a snark that proves I know a SHA preimage of the all zero string. So I know a value which hashes to the all zero string, which, if you interpret that bit string as an integer, is divisible by 3. Okay, super contrived. Let's talk about it. So what does it mean? We want to make a snarky program which holds exactly if I know how to provide answers to all the requests made by that program so that it executes without an assertion failure. So we want to make this program, in other words, pass all of its assertions in the case that this is true. Okay? So, right. So let's suppose we wanted to have this be as a constraint system. It seems difficult, right? I mean, I need to somehow come up with a constraint system which is satisfied if and only if SHA-256, hashes to a particular value. Then I need to come up with a constraint system that does division, and then I somehow need to stitch them together. So I didn't, of course, write any of the SHA-256 thing. That's something very complicated. But abstractly, if we sort of abstract away the definitions of things like SHA and division by 3, the way that you write the program is quite clear and quite simple, I think. So first, we would define SHA-256. Okay? Does it make sense? So it's SHA, it's a function. It takes a bit string of length, say 512, and it returns you a bit string of length, say 256. Okay? Yeah? Do people know what I mean? Who knows what I'm saying? Bit string. Sequence of booleans, bits. Okay. So now we declare a request, which is find a preimage. So given a bit string of length 256 and output, we expect an input, a bit string of length 512. Now we can sort of define a function which actually finds a preimage for us. Okay? Of course, it's not a real function, right? You can't just find a preimage to a hash function, right? That's the idea. That's the whole point. And yet we can sort of define a function which does, in some sense, find preimages as hash functions. How does it work? Okay, it takes in the input. It says, hey, I request that someone out there find a preimage to this hash. Then once, someone's going to put that in, let's call it x. Then I assert that SHA of x is equal to my hash, and then I return x. Okay? Does this idea make sense? So now we have like a function which takes in a hash and finds you a preimage. It does so by asking its environment for help, and then checking after the fact. Okay? Sort of, something, maybe. Okay. So now, let's suppose that we also have a function that, says, I assert this is divisible by 3, which just takes a bit string and checks it's divisible by 3. And now our whole program is just going to be find a preimage to the all zero string and then assert that it's divisible by 3. Okay, simple, right? Yeah.
Does it make sense to think of these assert statements like checkpoints?
Like checkpoints, how do you mean?
Like checkpoints in the computation of some problem?
Yeah, so somehow like the assertions are, well, yeah, so what do you mean exactly? I guess I don't quite understand.
Just like proof that you've made it X bar in some sort of computational program.
So, somehow, like, you probably want to have like an assertion for somehow like every step of the computation. So, you want to say like, I mean, it's hard to, yeah. We'll see an example actually in a little bit. Well, I think if people are interested, it's kind of interesting. This talk is maybe this is maybe for people who have programmed for SNARKS before. I'm not sure. Well, maybe we'll see an example, but as checkpoints, I'm not sure. I'm not exactly sure what you mean, I guess. Okay, and then, with the handling, okay, so this is how we use our handlers. We have this computation asserted divisible by 3. Now I handle any requests made by this computation by saying, if this computation happens to ask me to find a preimage, h, I'm going to look at my secret lookup table for h, and I'll respond with that value. Okay? So I have some secret lookup table of shop preimages, and I'm not telling you about. Yeah, okay. Well, okay, let's not talk about that. So, okay, so as I said, the number of constraints is still super important. So you have to make it easy for people to drop down to a low level of programming if you want to. And that's still very possible here. So let's say, can people see this board? It's a bit dark, isn't it? People can see it? Okay. Maybe I'll use a different color. So this is kind of a funny constraint system. I don't know who invented this. But yeah, so let's say you have some variables, x, y, and b, okay. And you want to make a constraint system. This is just kind of funny. Constraint system enforcing b is a Boolean which says whether x and y are equal. Does that make sense? So you want to come up with some equations so that those equations can only be satisfied with b being either 0 or 1, and if you plug in, if b is 0, you know that the values given to x and y were equal, and if b is 1, if b is 0, you know that the values given to x and y were not equal, and if b is 1, you know that the values of x and y were equal. Okay? So this is kind of a funny constraint system. So the way that you do this is you introduce actually like a new variable. Let's call it like inv, and you say b times x minus y should be 0, and inv times x minus y should be equal to b. And you should think about this on your own, that this actually works. I don't know who made this. Maybe Howard knows. But anyway, so you need to do this kind of low-level garbage where this is how you compute equality somehow, is using this constraint system. So you can still do that. You just request a new variables inv and result. I call this b, and then you can make your assertions just as before, and it's fine. But whereas here we had some massive constraints, here we expose a very simple interface. So now before it was like, oh, you have to make a constraint system. Now there's just like a function. It takes two field elements and returns you a bool. And inside there's some constraints which make sure it's the right bool. Okay? Does it make sense? So you can actually sort of encapsulate this into a nice functional interface. Okay. So yeah. So that's about all I'll say about this language for now, and then we'll see an example. I'll run it. There's a lot of benefits. I think it's similar to whatever benefits you have by programming in a high-level language instead of programming assembly. Even though it's still relatively primitive. Things are compositional, so expressions can actually be sort of assigned meanings rather than like this is just a constraint system. Because things are there's sort of simple semantics in terms of functions. Because there is a simple semantics in terms of functions, it means that one day it will be easy to write formal proofs about programs like this. Well, easy, by easy I mean possible, rather than here's a constraint system and maybe things interact in a weird way, maybe they don't. You can have sort of abstraction without having to pay the price. So as I mentioned with this like equality example, safer, easier to check, all that kind of stuff. We talked about this. Okay, so conclusion. I don't know if people are into programming languages. If you want to see typing rules, I can if you make me write them down, for this programming language. This is on GitHub. Here, github.com/o1-lab/snarky. We're hiring, so if people are into cryptocurrency or cryptography or functional programming or anything or whatever, please go to our website. It's I'll just tell you, it's little o number 1 labs.org. Another thing is I think this is something that hasn't been fucked up yet. So there's situations where all the dominant programming languages suck, right? Like mainstream programming. This is a very opinionated opinion, okay? But in mainstream programming, things kind of suck. In cryptocurrency, smart contract situation, now you have Solidity, this sucks. Here is a domain where there's not a dominant language yet. So this is an opportunity to make a language that doesn't suck, maybe. Maybe there is kind of a worse is better thing happening, where whatever is most familiar to people just sticks. But we'll see. Okay, so now I'm going to pause and do people have questions about what I just said? Sorry, maybe it was super confusing. I don't know. Anyone? Yeah, what's up?
So you guys are developing this language that you just went over now?
Yeah, so it exists as an embedded DSL in OCaml.
Okay. So what is the work that's being done then?
What are we doing? Yeah, so as I said, we're using our ultimate goal is to produce a cryptocurrency where where you don't have to accumulate history, right? So everyone can actually verify the current state of the world. You don't have to rely on whoever happens to be storing the state to do that. So right now, I connect to Bitcoin or whatever. I have to download 150 gigabytes, right? And then check it myself, or trust a third party who's doing that for me. In which case, it's not totally clear we're using cryptocurrency, or whatever. So we would like to have our cryptocurrencies be easy for everyone to verify. Everyone should be able to actually verify fully, this is how much money I have. This is if this transaction went through or not. Yeah? So a good way of doing that is to use SNARKS. Instead of showing someone the whole blockchain, you show them the proof that there was some blockchain, which explained the thing that they wanted to know. That's a complicated thing, so we made a programming language to make writing SNARKS easier. So that's what we're working on, this cryptocurrency, which is sort of instantly syncable, everyone can verify kind of thing. Does it make sense? Yeah. Yes. Any other questions? Okay.
If we were interested in being part of the software, what sort of background would be necessary?
Be a smart person who is interested, and I don't know, I'm not sure. So yeah, some nice, as I said, some nice. There are no hard and fast requirements. But if you're into functional programming, if you're into cryptography, if you're into distributed systems, if you're into programming languages, I don't know. These are all cool things. But really, if you're interested, please just talk to me, because it's more about who are you as an individual person, right? So I don't know. You had a question?
Yeah. I was wondering if you could really solidify why this is a tool is necessary for the work that you want to accomplish. This is not the end goal, right?
Yes, this is necessary for the following reason. The entire security of the cryptocurrency protocol that I mentioned that we're working on, which is you show us a proof instead of a blockchain, rests on the assumption that the snark that you produce proves actually what you wanted to prove. So if it proves something else, you're screwed, right? I mean, then people can make fake proofs, and what was the point of using proofs anyway? So you really need to have a very high degree of confidence in the correctness of the constraint system that you write down. one viable path to this is having high-level languages that you can actually reason about, more easily than a constraint system directly, which then compiles into a constraint system. Does that make sense?
Yeah.
Yeah.
I don't think like Berkeley's offerings kind of cover things like verifiability and composability and things like that. So like that sort of background is useful.
Oh yeah, yeah. So okay. I mean, like I think forget whatever words I said. All I mean is it's the difference between I send you a program in what's someone's favorite programming language? Oh, Camel. No. Okay. Any real answers? No. Okay. Sorry, just kidding. Okay. Well, even C, which is a terrible programming language, even C programming language. If I send you, I'm sorry. I mean terrible from the point of view of safety. Okay. It's of course fun. It's of course fun to program C sometimes. Riding motorcycles is fun. So, even a C program, right? Like, I can send you a C program that does something and you can read it and it's easier for you to understand as a human because there's concepts like functions and variables and stuff like that. Or I can send you an assembly program that's add this register to this register, move this register to this register, look up this address, et cetera, which is easier to understand than the C program, of course. Right? Which is easier to check if it's correct, the C program. It's the same situation here. If I just show you a constraint system, that's like if I just show you an assembly program. Does that make sense? So you want to have a high-level programming language just so you can actually really check if it's correct. Does that answer the question? Oh, okay. Other questions? Yes.
Have you guys done any benchmarking?
On
how big certain things are?
So it's a funny question because it's it's like in C, you can just put in blocks of assembly code. So if someone was like, oh, how fast is C? You could say, oh, it's as fast as the best assembly program that you write because you could just put in assembly code. It's the same thing. It's kind of the same situation here, which is what I was trying to point out with this equality example. Like anything that you can do just by writing constraint systems by hand, you can still do here. It just sort of wraps it up for you in a nicer way. So I'm never, people ask this question a lot. I'm never really sure how to answer it. The short answer is if you have a super optimized constraint system that you're sure it's correct, you can write a super optimized function that's exactly as performant.
Okay. I'm not really sure how the embedded part works. But,
Forget about the embedding. It's not. Yeah. Yeah. It's inessential. It's only there because I'm too lazy to write a parser and a type checker. Okay. Other questions? Yeah.
Non-technical.
Okay.
How did you get involved with this effort yourself?
So let's see. Well, okay. So I was a grad student here, and I started this project. So I guess I started the project. but I was a grad student here studying cryptography. So that's how, sort of, in some way. Okay. So now I'll show you guys a little example, just kind of for fun. We'll run it. Oh, cool. So, let's have an election. Okay. So let's say we want to do this kind of election thing that I mentioned. This is a crappy way to do it, but it's simple. So that's why I'm explaining it. This is not how you would run an election using SNARKS, but this is a way. Okay. So here's the setup. Let's say that I'm going to order pizza for everyone. I'm not. But suppose this were the case. We want to decide what toppings we're going to get. And we're going to decide between, let's say, pepperoni and mushroom. I'm a vegetarian, so I apologize if it goes the mushroom way, or pepperoni way. I will be upset as well. But these are our choices. So we're going to, of course, have a democratic election. Everyone will vote. Then we'll count up the votes, and a winner will be decided. But let's say people don't want to reveal to each other which one they voted for. Okay, maybe people are I don't know, are private about what pizza toppings they prefer. So what we're going to do is the following. Everyone is going to, you can imagine, here's how we run it physically. You'll take your vote. You'll put it into an envelope. Okay? We'll put all those envelopes into a box. The box will be given to me. I'm going to open all the envelopes, so I'll know what everyone likes, but oh well. And then I'll count up who wanted what. Okay, so I know, I guess, but no one else knows. So if you can trust me to keep your pizza preferences secret, we could do that. But that's boring. Wouldn't it be cool if we could use cryptography to somehow prove? I could be lying, right? Like you give me the votes, but I could just like do nothing and just say the winner was mushroom, right? You see what I mean? So it would be cool if like we use cryptography to somehow prove that actually I ran the election fairly. I counted each and every one of your votes, and the winner was whatever it was. So that will be the goal. So this is like a running example. Okay, so this is kind of the program. Let's see. So okay, so it takes as input here. Oh, maybe can we turn the slide off? How do I? This? No. Okay. Maybe you know better than me. Dark screen. Oh, cool. So okay. So this is the program. It's going to take as input like an array of opened ballots. Okay, where an open ballot will be basically a vote. Oh, I forgot to explain. Okay, so who knows what a commitment is? Does anyone know what that is? So a commitment is the following idea. Before you guys vote, before you give me your votes, you're going to commit to them publicly. You're going to somehow publish some information which binds you to this vote, but doesn't reveal which vote it is. Okay, it's sort of like an encryption or something of the vote. Okay, and the way that you do that is by you pick some random value called a nonce. You take your vote, you stick the nonce and your vote together, and you hash them, and you publish the hash. Does that make sense? Because you can't go back on it, right? You can't find another preimage to that hash. So that's called a commitment. It's sort of like sealing an envelope and like putting the envelope on the table, okay? And no one can open the envelope, well, except you, if you know the opening. So okay, so a ballot is going to be an open commitment, so a nonce and a vote, okay? An open ballot will be that. A closed ballot will just be a hash, a commitment, yeah? So first what you do is you compute these commitments. We're going to define a function called checkWinner, which checkWinner is going to be like a snarky program on commitments and claimed winner, and it's going to check that this is really the winner according to the votes corresponding to these commitments. Okay. So let's look at checkWinner. Okay. What do? You compute W, the winner, according to these commitments, and then assert that W is equal to the claimed winner. Okay, straightforward enough, right? So now if we believe that winner correctly computes the winner of this list of commitments, then this is what we wanted to prove, right? That this assertion passes. Right? So okay, so now let's look at the compute winner function. So basically, what we do, we go over all the commitments, over all the closed ballots. Somehow we open them. We map over the list and somehow open every closed commitment. Okay? Of course, you can't open a commitment necessarily. And then you count the number of somehow you count the number of votes which are for pepperoni. You check, you say pepperoni wins if the number of pepperoni votes is bigger than half, and you return, if pepperoni wins, then you return pepperoni. Otherwise, you return mushroom. Okay. So that's how you compute the winner. You just do simple majority bias toward mushroom. Okie dokie. Now this is count pepperoni votes. Oh, this is kind of a confusing way to write it. Oh well. Let's not look at count pepperoni votes. This is count pepperoni votes. You basically, if people know it, fold is in like functional programming languages. Sometimes it's called like reduce. You sort of loop over all the votes, and you check which ones are for pepperoni, and you increment your counter if it's for pepperoni. Okay.
Wait, so if you don't know like the nonce, how would you
Open the commitment, right?
Yeah, how would you open like
Yeah. So the idea is this like request thing. So let's look at right. So open ballot, as you said, is like an impossible function, right? It's supposed to take as input a commitment and return the opening to the commitment, right? But if you don't know the nonce, you can't do that. So the way that you do it is you say, I request someone please put in my hand an opening to this commitment. And then I request an opening to this commitment such that if you take the open commitment and basically hash it, I'm going to get the value, the actual commitment. Okay, so I'm requesting, the way that I open a ballot is I non-deterministically request, I put my hand out, I request that someone put in an opened ballot in there. Now inside, I say, I assert that that actually the thing that someone put in my hand does actually correspond to the value that was committed to.
So do you just sort of keep taking requests until you like open every commitment?
Yeah, so for each commitment, I'm gonna request that someone open the commitment, and then outside, because I actually the person running the computation, I actually do know all the openings. You gave me all your openings, say. Then I can answer those requests. Does it make sense? Yeah.
To request the nonce as well?
Huh?
You have to request the nonce as well?
Yeah. So you have to request the vote in the nonce, which corresponds to the commitment, and then you check that indeed they do correspond to the commitment. That's how you like open a ballot. Okay. So anyway, this is kind of the example. It's online if you want to see it. And so yeah. So here's how we like handle it. As per your question, we say, okay, if this computation makes a request for opening a ballot, respond by providing the opened ballot in my secret array of ballots. Okay? And then the zero knowledge, I forgot to say, these things are like zero knowledge, right? Which means that the values that are provided are sort of hidden. Okay, so that's a little example. We can run it. Maybe it's fun. Okay, so some loop snark crap happens. So let's see. So here were all the ballots. This was a nonce. This was a nonce. These are all the nonces. Here are all the votes. Here are all the commitments, and the winner was pepperoni. And we produced a proof, and it verified. Okay. Okay. That's I don't know how interesting it is to see me run that example, but maybe it's cool to know that at least it's possible to run. Yeah.
Expand a little bit in like more details. How does the verifying part work? Kind of like a little bit.
Oh yeah, it's
In terms of like basically like make sure that was the actual work.
right. So that's right. Okay. So as I kind of alluded to, there's sort of there's sort of this like kind of this is 1 second. There's sort of this like composite process where we write a program in the snarky program. The compiler turns that into a constraint system, and then somehow a snark or a proof is produced. Okay? So there's sort of two things going on here. One is like we need to make sure that the constraint system we produce like accurately reflects the meaning of our program, and then there's like in here goes the cryptography, which is somehow producing these proofs that someone knows a satisfying assignment to a constraint system. There, it's a bit complicated. Roughly speaking, the way it works is the following. Okay, so is it clear that we sort of reduce our problem to the problem of proving that I know a satisfying assignment to a constraint system? Then the question is, okay, now how do you produce that proofs that you know a satisfying assignment to a constraint system? So say again?
Someone votes, right?
Yes.
My question is mainly in the part of like, so how do we prove that vote is real? So you have the commitment, right?
So maybe I forgot to say, the proof that I present, the statement that it verifies against is everyone's commitments. So there's a procedure, you plug in the proof and everyone's commitments, and it says true or false. And so the idea is like it should say true only if I open all those commitments and then sum up all the votes, that it goes pepperoni or mushroom. Does that make sense? Oh, sorry, it takes all the votes and the proof and also the winner.
So the commitments come from some other place, and then they're going to be compared to the results that you're going to basically.
So you guys are all going to make your commitments. You're going to put them on the internet. Then you're going to, oh yeah, and then you can check the proof against the list of commitments and also the claimed winner. And you can check that your commitment, is in that list and so on. So you know that your vote was counted and all that. Okay. Yeah, so that's pretty much all I have, I guess. Oh, question? Someone? No, okay. Anyone have any more questions?
All right. Well, thank you. So, I guess we're gonna have our last lecture tomorrow. I think we've confirmed Sunny is gonna be presenting.
From Cosmos will be lecturing on interoperability and probably ABCI and some other stuff.
Okay, cool stuff. See you there. Thank you, man.
Yeah, sure.
Cool.
My pleasure.
I hope this worked.
What's that? Oh,
the
yeah, me too.
yeah.
Oh, you thought so? Oh, great.